Good morning. This is Joe Morosco again, and this is part 3 of our 3-part series on making decisions and handling uncertainty. In this part, we're going to answer the last 2 of the 3 questions that are most frequently asked. Where we left off at the end of part 2 is to have 2 expressions for the Bayesian update. And what we're going to do here is come back from our medical example to the general Bayes formulation. So the equations or the formulas shown in the baby blue box and the baby pink box are for any test of any statement. It's not limited to medical at all. And we notice that, we've put some icons to illustrate what's going on here. The pan balance icons show that in one case the balance will be in one direction, in one case, in the other case, the other direction. And also on the left, the meat grinder, we turn the meat grinder in one direction if we got a positive result, and we turn it in the other direction if we got a negative result. We have a very, very versatile meat grinder. And if we ever get confused about what's going on, we can always check our results, noting that the probability that a statement is true plus the probability that the statement is false always has to add up to 1. So we're going to return now to the question of how the iterative update works. If you recall in the previous example, we started with a prior probability of having the disease of 0.3, and then we turned the crank and got the result of 0.714 by just using the baby blue box equation. Now what we do is we take that result and we plug it back in for the next iteration. So the probability that the patient has the disease is now 0.714. And we do our next test using that as the starting point. And we keep doing that. Now there's 2 points I'd like to make about this equation and this process. When we go to do the next test, the factors that are in the oval here are going to be different because it's a different test. And this is, in effect, where the weighting factor that we've been talking about all along comes in. This weighting factor is different for every test. So we have our new starting point here, and we're going to have a different test characterization table, and that will lead us to have a different factor inside the oval. The second thing I'd like to remind you of is if on the subsequent test we get a negative result, then instead of using the baby blue box, we have to plug the 0.714 into the baby pink box, because we got a negative result on the subsequent test. One caveat here is that this gives you the conceptual framework, but in actual practice, there's a few messy details. And that comes from the fact that we usually do not have the test characterization table that is at the core of all of this. And we often have the information that you get from that table, but we get it in a different form because there's lots of different ways of expressing the imperfection of the test. So even if we don't have the test characterization table, as long as we have the equivalent information in a different form, we can still use the Bayesian update. It's just that there are a few more messy details that we have to do. But we're not going to dwell on that right now. So we come now to the last remaining detail, which is what I call the pesky prior. And that's the initial prior probability. And many people agonize over this for the following reason. Their logic is that the prior probability, the initial prior probability, contains all that we know about the statement. And I should point out that it also contains all the negative evidence that the statement might not be true. And most people say, well, gee whiz, if I get the initial prior wrong and everything builds on top of it, how can I ever be sure that the answer I get is a good answer or not? Because I'm building on a foundation of sand. And we have to address that problem. And the answer is that while the prior probability is important, it's the accumulated weighted evidence that determines the outcome. Remember, we said at the very beginning that we needed a process where you could start from any place. And we're now going to demonstrate that that statement is true. So for our demonstration, we're going to consider two scientists who are working independently in two different labs. Okay, there's one scientist in New York and one scientist in San Francisco. And scientist Smith assigns a probability that some statement is true of 0.3, which means that he believes that it's more likely that the statement is not true because his prior probability is less than 0.5. Scientist Jones, okay, on the opposite coast, believes that the statement is true and assigns a prior probability of 0.7. Now, that's a 40-point difference, and that's huge. In real life, we would rarely see two scientists disagree by that much. Usually one is going to be a little bit above 0.5 and one is going to be a little bit below 0.5. But to make the point here, we're exaggerating that difference. And now what we're going to do is we're going to ask both scientists to independently perform a series of 5 tests on the statement. And those tests will be done sequentially. So here are some tables. And we notice that the tests have a mix of positive and negative results, and also a variety of strengths. Some tests are stronger than others. And in fact, we're even going to show you the likelihood ratios in the 2 columns called LR, and those numbers reflect the strength of the test. We're not going to go into any more detail now except to say that we use those numbers to get numerical results. And what's important here is that both labs get the same results from the same tests. The only difference here is that Smith does the tests in the order we gave them to him. Jones, on the other hand, she makes the following statement. She said, well, look, if this Bayes process really works, it shouldn't matter what order I do the tests in. I should ultimately get to the same final updated probability if I get the same results from the same tests that Smith did. As long as we both do all the tests and get the same results, we should ultimately get to the same answer. And here are the results. The first table here on the left is just the table from the previous slide in a more condensed form, but we've just brought that table forward. And the second table, which contains the probability that the statement is true, notice that we start out with a prior of 0.3 for Smith and 0.7 for Jones. And we can see that here in the graph, 0.7 for Jones and 0.3 for Smith. And so this distance here is the initial disagreement between the two priors. And then they perform the tests, and each time they get an updated prior, that becomes an updated probability, that becomes the new prior for the next test. And so all we've done here is run the update process 5 times for each experimenter. So there's 5 results. And what we notice is that at the end, after the 5th test, we have convergence. The 2 results are pretty much identical. So we go from initial disagreement to convergence. Now, it's almost as though there was some underlying truth, and both of the experimenters are seeking that truth. And at the end of running a number of Bayesian updates, they arrive at that truth. And what that tells us is that regardless of where we start, we eventually get to that truth. And essentially this is telling us that the prior probability is important, but it's not critical. If we do enough tests, ultimately we'll get to the right result. So the moral of the story is we always have to start somewhere. We use this initial prior to summarize all of our knowledge or all of our information, and then we perform a series of tests. And at any time, the current prior, which is the last updated prior, is our best estimate. So we always have an answer at any time in hand. After we do a lot of tests, we're going to discover that the initial prior doesn't matter. It gets submerged. And we'll get convergence either towards 0 or 1. Now, if our tests are weak, if they're not strong tests, we may converge to a different value, like 0.8 or 0.2. And that's because our tests aren't strong enough to force us towards 0 or 1. But when we have strong tests, they accelerate convergence. And all of this demonstrates to us that the Bayesian weighting scheme for doing the update operates as intended. So we're coming close to the end, and what I'd like to do on this slide, I always like to have one slide that sort of captures everything important, so that if you want to come back and jog your memory, you can always come back to that one slide, that recap slide. So we have a lot of stuff on this slide. It's kind of crowded, but it's crowded intentionally because we sort of want to recap everything. So we have the 7 sentences that describe the process. And then over here on the right, we have our diagram of the process. We've got our baby blue box and our baby pink box. Those are the 2 update equations for the positive test result and the negative test result. And then here along the left, we've got a bunch of icons that hopefully will help jog your memory about a lot of the ingredients of the process. And down here, as the summary of the summary, if you will, is the notion that the accumulated evidence through doing experiments triumphs over our prior initial belief. And that essentially is what the scientific method is all about. No matter where we start out, if we gather enough evidence, we'll get to a result regardless of where we started. Now I have 2 books, if you're interested in going further, that I've read and I've enjoyed. They're written for the general public. They're not specialized tomes. One is more of a history. That's the first book. And the second book is written by Nate Silver. He's the person who has the 538 website. And he makes extensive use of the Bayes method to make predictions. Both these books are on Amazon, and I highly suggest them. So I hope you've enjoyed this 3-part series. I hope you come back to it. I've tried to make it as simple as possible. And I hope in the approximately 1 hour that you've spent with these 3 YouTube videos that you've gotten a pretty good grasp on making better decisions by using the Bayesian update and the Bayesian process. Thank you very much.